Welcome back. This is the final lesson in our series of lessons on the bubble sort and the insertion sort. In this short lesson, we'll look at the ways that we can make small changes to the sort algorithms to make them go faster. So what does it mean to optimize a sort algorithm? How can we optimize the insertion sort? How can we optimize the bubble sort? And once we've done some optimization, how can we check the effect that it's had on the speed of the algorithm? Optimizing an algorithm doesn't mean changing it to a completely new algorithm. It means making a small change that will reduce the number of operations that the computer has to do. By reducing the number of operations, we'll make the sort complete its job more quickly. We've already seen a way to optimize the insertion sort. Do you remember what it is? What we do is we break the backwards for loop when the item that's being passed backwards reaches its final position. That is when it is no longer smaller than the values that are behind it. So let's have a look at that. The break command, if we build that break into the loop, that will speed up our work. We can do something similar in the bubble sort. So here's the bubble sort algorithm. To optimize that, what we do is we store every time there's a swap, we store the position. That means it will end up storing the position of the most recent swap. When we're going forwards through the loop with the for loop that traverses the loop, we can stop at the most recent previous swap, because if there were no swaps further along the list last time, there won't be any swaps this time either. So you could take a few moments to think that through, or just take it on trust, because it does work. Let's see how that would look if we're actually programming the bubble sort. So in this example, I've used that idea to optimize the bubble sort. First of all, I've created a value called stop, and this will tell us when the for loop can stop. There are lots and lots of for loops going forwards through the entire list, traversing the entire list in the bubble sort. The original value to stop that for loop is the length of the list -1. The program will count up to this value and then stop. But look what I've added inside the loop. If there's a swap, we store the position of the swap as the stop variable. Now the next time the forward for loop happens, it will stop at the position of the final swap. And as more and more of the list gets sorted, the position of the final swap will get earlier and earlier in the program. This saves the computer from carrying on traversing the list. And remember, the list might have 1 million items in it. So it saves the computer from having to constantly go right to the end of the list. It only checks the part where there are still swaps left to do. I strongly recommend you try this and see if you can notice the difference it makes, particularly when you're sorting a large list. However, that's very impressionistic, just having a feeling that it might be a bit faster. A very good way to check the effect of any optimization is to create a counter variable, and that will increment every time that there's a loop. And in this way, it will count how many repetitions there are in your sort program. And remember, the fewer the number of repetitions, the quicker your sort will be finished. and then you can print out the final value and compare different sort algorithms, or compare the number of operations before and after you've done your improvements. So let's have a quick look at how we might do that. Here is the that same bubble sort that we were just looking at, and I've added a counter. The counter starts at 0, and inside the second loop, so I'm putting it inside a loop, so it counts the maximum number of iterations. Inside the second loop, I'm incrementing that counter by 1. So it will count the total number of loops inside loops that are required to complete this algorithm. And then at the end of my program, I'm printing it out. Obviously, I could do this with any sort algorithm, and I can do it before and after I add any optimization. So to recap, you should know what optimization means. When we optimize a sort, we make a small change which reduces the number of operations required to complete the sort. We can optimize the insertion sort very easily by adding a break command. And we can optimize the bubble sort by storing the position of the final swap of any loop and using that as the end value of the loop. And we can check the effect of optimization by building in a counter to count the number of loops inside loops, and we should see that number going down as we optimize the sorts. So remember, if you're my student, we've got access to a big long list called town list, but any of you who are watching this, you can just create a big list of random numbers and sort it using any algorithm you know and count the number of operations. Then optimize it and count them again and see how this changes the number of operations that are required. You should see a significant improvement. Okay, so this concludes the series of lessons we've had on two simple sort algorithms, the bubble sort and the insertion sort. I'm now going to turn to two more complicated, more challenging algorithms, which are called the merge sort and quick sort, and we'll look at how to program those as well. Okay, so bye for now.